In this video, I'm going to show you the architecture I'm building to integrate artificial intelligence into the kind of software I've been developing for years: desktop applications. The architecture is built around three layers: the application layer, the database layer, and the AI layer. The AI architecture itself is divided into two layers: a generic abstraction layer that allows every model to be treated as if it were the same model, a separate implementation layer for each specific model provider. The database layer follows the same approach and is also divided into two parts: a generic abstraction layer that covers the ISO SQL standard, a separate implementation layer for each specific database engine. As for the application itself, the architecture is built around three core ideas: modularity, connectivity, and extensibility. Instead of developing a different application for every specific use case, I chose to build a centralized infrastructure around a single executable, a desktop application. The main application, which acts as the central orchestrator, it's an MDI application. The AI console, this is where I interact with the models, but it's also where I manage and inspect the entire context. And finally, an empty workspace where I can freely build dashboards using interconnected components. Components follow a client-provider model. A provider offers services, and a client consumes them. Each client-provider relationship is unique. This keeps connections between components simple, both for the system and for the user. A component can be both a client and a provider at the same time, depending on the services involved. The configuration of each dashboard can be stored either in JSON files or in a database. These configurations contain not only the layout of the dashboard, but also the state and contents of its components. The application can also connect to other instances through MCP. This allows component relationships to extend beyond a single application instance and reach components running remotely. The AI layer is not centered on the model. It's centered on the context. The context includes system instructions, user and assistant messages, documentation and attachments, and the tools that models use to interact with both the application and the user. The application uses its own internal format to define all of these elements. The context can be edited, stored in files or databases, and reused across different scenarios. This context is then translated into the specific format required by whichever model we're using at the time. So when it comes to AI, the goal is simple: complete control over the context. Or, in practical terms, complete control over token usage, cost, and efficiency. SQL can be used in the traditional way, as plain text sent directly to the server. But it can also be compiled and transformed into objects that can be manipulated programmatically, opening the door to a lot of additional possibilities. Each dashboard can include a special component that acts as a dashboard-specific AI console proxy. The other components inside the dashboard can subscribe to this proxy by adding controls to their own toolbars, allowing them to be enabled or disabled individually. For each component, it's also possible to enable or disable the specific elements that contribute information to the context. For example, a component can contribute a portion of the system message, a short identity description that becomes part of a shared context message describing the participants involved in the current task, a component-specific message, one or more APIs that the assistant can use through function calling to interact with that component, a JSON description of its internal user interface structure, documented so the assistant knows how to interact with it, component-specific documentation stored in JSON format and accessible incrementally, a snapshot of its current state as an image, any other resources provided as attachments. Inside the console, we can view and edit every context message that will be sent with a request. Chat messages can be temporarily disabled so they are ignored during processing without being removed. They can also be deleted completely if they're no longer needed. We can even add function calls manually, as if they had been generated by the assistant itself, providing examples for more complex use cases. It's also possible to remove all messages before a specific point, or everything after it, allowing a conversation to continue from any point in its history. At any moment, we can estimate how many tokens the current context consumes. The console also includes several tabs in addition to the active chat view. One of them is the Pending Requests tab, which is used when we want to launch multiple requests that we expect to take a significant amount of time. Each request runs in its own task, so the application never becomes blocked while work is being processed. Once those requests are finished, their resulting messages can be inserted anywhere in the conversation. Another tab is dedicated to context version management. Every significant change made to the context automatically creates a snapshot of the previous state that can be restored later. Restoration can be complete or partial. A previous version can replace the current context entirely, or it can be inserted at any point in the message chain. The Tools tab is where we manage several different aspects of the system. From here we can manage the application's own context contributions, including its system message and a short identity description that becomes part of the shared component identity message. The general APIs exposed by the application itself. I refer to these groups of functions as services. The APIs exposed by individual components, which can also be enabled or disabled from here. Additional tools such as web search, document-based RAG search, code execution, and more. This next feature is something I call a Gnome. Some components are fairly complex and require a significant amount of documentation. A Gnome is a dedicated LLM that can be assigned to one of those components and work with a separate, specialized context provided by that component. The main LLM can delegate work to these Gnomes, which perform their tasks in the background. Gnomes don't maintain memory. Their context is disposable and used only for a single task. They receive a request, do their work, and return a result to the caller when they are finished. This allows us to use smaller and less expensive models for intensive but relatively simple tasks, while reserving the more capable and more expensive models for problems that require deeper reasoning. Components that support Gnomes expose a dedicated button in their toolbar, allowing their use to be enabled or disabled whenever the console permits it. When a Gnome is enabled, the APIs required to interact with it are automatically added to the context. Every time a new dashboard is opened, its context contribution settings are automatically added to the console, together with the settings for all of its components. This means we don't need to include an AI console proxy in every dashboard, although using one can be more convenient because it lets us manage those options without switching tabs. When a dashboard is closed, its configuration is automatically removed from the console. Finally, this last tab records the messages sent by the application itself. These messages are usually errors, warnings, or useful information for debugging problems. And of course, everything I've shown here can also be written to log files or stored in databases, if the corresponding option is enabled. The goal is to build a universal and extensible infrastructure that can also contribute information about its own source code to the context. That way, AI assistants can help extend and debug the system from the inside, as part of the system itself. In future videos, I'll go deeper into each of these ideas.